Welcome to the Remediation Technologies Blended Learning Suite. This is the In Situ Bioremediation Module 2 design. This subject is written and presented by Alan Thomas of ERM. I've structured the model in two parts. The first part is looking at some of the underlying fundamentals behind In Situ Bioremediation design. The second is looking at the process itself. I'd like to begin by just outlining what we mean by in situ bioremediation. The key features are it is obviously a application of biological processes. The treatment occurs in place within the subsurface, and fundamentally we've been engineering the subsurface to optimize one or more aspects of microbial activity. There's a wide range of microbial diversity in the subsurface and a range of contaminants as well, and as a result there are a large number of variations in the application of in situ bioremediation. The most commonly applied commercially, I believe, are aerobic processes where we're looking at hydrocarbons, TPH, BTEX, phenols and polyaromatic hydrocarbons as being key contaminants of concern, and also anaerobic processes where chlorinated solvents are the main focus, but also some pesticides, nitrates and metals. And I think that knowledge and understanding of these applications are applicable to a wide variety of scenarios. This is just a reminder of some of the microbial processes that you should be familiar with. It's following some of the background reading. Essentially, again, it's emphasizing the microbial diversity that's in the subsurface and the different metabolic strategies of organisms that we are able to utilize in situ bioremediation, from simple aerobic degradation using oxygen through various stages of reduction, which may include the use of alternative electron acceptors including nitrate, sulfate, iron, etc., right through to the anaerobic processes, methanogenesis. And of particular interest for chlorinated solvents is the process of dehalo respiration. But effectively, as I've said, a wide diversity of microbial processes that we can optimize. Two key aspects underpin microbial process design. It's not a black box as many people kind of think, but it really is an engineered kind of process. Two essentials to that are the reaction stoichiometry, and that's basically, in simple terms, saying the amount of reactants you need to effect a microbial process. So it's really the balance, if you like, between adding oxygen compared to the mass of hydrocarbons that you have present. And the second thing is the reaction kinetics. How quick is the reaction occurring? And I think you need to balance those two elements in underpin really any in situ bioremediation design. Just emphasizing again the stoichiometry aspects. Again, you hopefully have read about this in some of the background reading. But effectively, through stoichiometry, we are able to work out a mass balance of the the quantities of reactants and products, and so we can really engineer the amount of substrate or electron acceptor that we add to the subsurface to stimulate and effectively degrade the mass of target compound that's present. The more mass of electron acceptors that we can add, typically the more degradation that is possible. But we should emphasize, or I should emphasize, it's not just the mass of contaminant that may consume some of these electron acceptors. There may be other non-target compounds that you've got to be aware of. So things like natural organic carbon or even reduced or inorganic species. So the design process has to take into account all these aspects really, but it should be a reasonably well defined kind of process and be subject to some kind of basis for the remediation design. Similarly for anaerobic systems, then we can also calculate the amount of donor dosing requirements as well, using similar principles, this time looking on hydrogen or electron equivalents really, to optimize the hydrogen production in the subsurface and in turn then optimize the reductive dechlorination process. And various electron donors will give you various hydrogen equivalents, and it'll be a matter of balancing which one works for your site. As I mentioned, biodegradation rates are a critical part of in situ bioremediation design. Bioremediation is occurring at a set rate, and unless you have the residence time within a reactive zone or within the subsurface to allow that reaction to proceed completely, then you may not get full degradation or optimized degradation of your compounds of concern. So while we can do kind of qualitative assessment of biodegradation rates, very often we also look at quantitative assessment in remediation design to try to optimize the design of the process such that it is emphasizing or reducing biodegradation rates, maximizing biodegradation rates. Very often biological processes follow first order reaction kinetics, where the rate of degradation of a substrate is proportional to the substrate concentration. And this graph really summarizes what we're trying to do. It's just showing the difference between optimized anaerobic and aerobic half-lives. And then clearly, if we are trying to get rapid degradation within the subsurface, then getting near as possible to the optimized aerobic half-life is our main kind of aim. And so we use this data in remedial design. The main controls on bioremediation rates in the subsurface are a mixture of environmental and contaminant specific factors. The environmental factors are listed there, and as you can see include things like temperature, the natural population of microorganisms that may be present, nutrients, respiratory substrates, and the extent of natural organic matter as well, which may be kind of competing in degradation rates. And the contaminant itself is obviously clearly important, both its concentration, the mixture, its physiochemical properties, its distribution within the subsurface, and whether it's sorbed or not to the matrix, and ultimately its bioavailability. And typically we found that the speed of biodegradation is constrained by a single or a limited number of rate-limited factors, and the whole approach to bioremediation is identifying those factors, removing the bottlenecks, and really allowing the process to proceed at an optimum rate as is possible. So the requirements for bioremediation processes are really that, again, the contaminants are biodegradable or biotreatable, and importantly bioavailable under the prevailing conditions. Biodegradation is a process that occurs in the aqueous phase, so we need our contaminants in the aqueous phase for bioremediation to occur. So they must be dissolving or be capable of being actively dissolved for bioremediation to really work properly. Clearly, as I've just mentioned, we need the degradative microorganisms, contaminants and additives in the same place at the same time. It's bringing all these elements together in situ, in the subsurface. That's a critical element. And then we must make the environmental conditions, either pH, redox, temperature, nutrients, etc., conducive to the desired biodegradation process. And finally, there should be no inhibitory factors. So the strategies for enhancing bioremediation are either through supply of electron acceptor for aerobic systems, and this can include oxygen or nitrate or sulfate in anaerobic systems, Or for things like reductive dechlorination, we're looking at electron donor, and these are typically various organic substrates that we'll have a look at in a few slides. Also, we may be seeking to add nutrients, optimize pH, and occasionally as well we may be looking at bioaugmentation, which is the introduction of microorganisms to the subsurface, and again I'll talk a little bit more about that later on. But ultimately as well then we need a means of delivery to the subsurface, as we said, getting these things into the ground in the right concentrations where the contaminant is, to really optimize biodegradation. So for aerobic systems, usually there are a range of kind of strategies, really, a whole kind of diverse range of strategies for adding oxygen to the subsurface. In the unsaturated zone, we can use technologies like bioventing, which is effectively just the injection of air or oxygen into the subsurface to promote in situ biodegradation in the subsurface. In the saturated zone, we can dissolve oxygen and nutrients in water and inject them. We can do gas injection or sparging or gas diffusion, or we can use solid compounds, solid oxygen release compounds. So 3 physical ways there of actually introducing oxygen into the subsurface. Each of these oxygen delivery systems has various advantages and disadvantages. This table is just summarizing the oxygen delivery efficiency and really emphasizing that if you're injecting or adding something in the vapor phase in terms of oxygen delivery, then it's a much more efficient way of adding oxygen mass to the subsurface compared to, say, re-injection of aerated or treated water, where you're really limited by the solubility of oxygen in the subsurface. So each of these technologies has a different ratio, if you like, in terms of oxygen delivery efficiency. But really the choice about which one is suitable for the site will be dependent upon site-specific conditions, and there may be, as well as technical factors, there may be economic and timescale reasons for choosing one oxygen delivery system above the other. And I do think it's important to look at the overall life cycle assessment of costs, not just the cost of oxygen supply. You've got to look at it in the overall site context. So for anaerobic systems, then we can again use some electron acceptors, nitrate and sulfate. I think sulfate is increasingly being looked at as a potential alternative for enhancing in situ biodegradation of hydrocarbon contaminants. But I guess the main anaerobic systems that are being promoted or used at the moment are the use of electron donors, particularly for reductive dechlorination of solvents. And again, there's a spectrum of approaches in relation to the use of these electron donors. Basically, they're classed in a number of ways. There's a range of soluble compounds, and the benefits of those, I guess, are ease of delivery in terms of injection into the subsurface. And they can include a range of volatile fatty acids, things like lactate. They can include soluble carbohydrates, things like molasses. Alcohols have been used, including ethanol, and you can see a whole range of other soluble compounds there. And then there's another group really that are classed as kind of insoluble compounds, and I suppose their benefit is that they kind of persist in the subsurface and maintain anaerobic conditions over a longer kind of period. And again, you've got categories there, then things like the polylactate type compounds, things like HRC, things like vegetable oils, and emulsified vegetable oils as well. And very often you may be kind of mixing substrates to get a mix of an initial kind of soluble flux followed by a long-term release, slow release of a less soluble compound. So as I said, really what I'm trying to emphasize is a whole range of potential alternatives and potential strategies here for electron donor delivery. The final class really is things like solids, and there's been a lot of interest in using very simple kind of materials, things like mulch, which can be used very often in shallow kind of situations to create shallow anaerobic kind of barriers, if you like, in the groundwater plume, and these mulch barriers can include things like wood chips, leaves, compost. Direct addition of hydrogen gas has been proposed, I think, in a number of technologies. And then really there's a whole range of other potential kind of options, and really any kind of biodegradable cheap material could be used, obviously subject to regulatory approval and regulatory agreement. But effectively, as really again what I'm trying to demonstrate is that there's this whole spectrum of potential approaches. And the reason for this difference is that they all kind of differ on the way they ferment and produce hydrogen. So it's clearly down to develop an understanding of what works best in a given kind of scenario. And again, very similar to the oxygen delivery scenarios, there's a whole range of factors that may influence what you're going to be doing at a given site. The cost effectiveness and availability of a given donor, its ease of application given the site hydrogeology, what you're trying to achieve, and whether persistence is a key variable that you want to enhance or not. And as I've already mentioned, regulatory issues as to what governs could be added to the subsurface in any location. I just wanted to add a little bit more about the advantages of anaerobic bioremediation, because I think it is a emerging technology and maybe a little bit less understood than the traditional aerobic biodegradation. The key thing, as I've mentioned, is that it's focused predominantly on chlorinated solvents. It results in destruction of contaminants. It may have lower capital and maintenance costs associated with it than some of the other more traditional technologies. It's applicable to all chlorinated ethenes, and methanes, and it is compatible with natural attenuation processes as well. It has been used to address DNAPL source zones, but it will result in increased dissolution of those source zones, and in fact that's what it's trying to do. It's trying to, or rather that's what the result of injection or optimization of anaerobic degradation is. It's really creating a dissolution gradient that's resulting in the increased removal of the residual NAPL into the dissolved phase where it's degraded. However, there are a number of disadvantages. It's not a simple biological process. You can't apply it at all sites. As I've said, you may be seeking to optimize the degradation of DNAPL, but DNAPL may also limit the success of the results. It's got a long time frame typically, and a key issue is potential incomplete dechlorination. So rather than getting particularly complete dechlorination through to ethane, you may get accumulation of intermediates like dichloroethane, DCE, and vinyl chloride, VC. The process itself may result in a degradation of water quality. There may be organic byproducts formed, and there may be solubilization of metals, and there may also be production of potentially hazardous gases as well. Effectively you're creating a very strong anaerobic environment, so you'd expect to see methane gas being produced in the unsaturated zone, potentially hydrogen sulfide, and as we've mentioned, vinyl chloride as well. I'd like to continue now by looking at the differences between biostimulation and bioaugmentation, as this is often a subject of some debate. Bioaugmentation is essentially the introduction of organisms to the subsurface to undertake remediation, whereas biostimulation is relying on the presence of naturally occurring organisms. Biostimulation is well proven and demonstrated for hydrocarbons. Typically organisms are present with the capabilities to undertake the degradation of the contaminants of concern, and in the bioremediation process we need to add either oxygen, nutrients, etc. to stimulate these organisms and promote and optimize degradation. Bioventing is a good example, where effectively we're looking at oxygen as being the limiting factor, and so through the introduction of air alone we're able to stimulate the in situ microbial population. As I've mentioned, bioaugmentation is the addition of organisms to the subsurface, and this slide is summarising a whole range of issues that have been raised in respect of bioaugmentation. Typically, key limitations have been a fundamental requirement to see whether there is a need to add organisms, whether we can track those organisms and really isolate what the benefits are. Recent interest in bioaugmentation has been in respect of chlorinated solvents. D. halococcides is a unique organism that's required for the complete reduction of chlorinated solvents, and the interest in bioaugmentation has been stimulated by improvements in molecular biology that allow better identification and tracking of added microorganisms. This technology has been successfully demonstrated and is commercially introduced. Just to summarise the reason for this interest, in some chlorinated solvent sites, dichloroethene and vinyl chloride can accumulate as degradation products and not proceed the whole way through to the ultimate products of ethene and ethane. These two slides show this phenomenon in a little bit more detail. The upper slide just shows the long-term accumulation of DC, very often termed dechlorination stalling, and possibly could be a candidate for bioaugmentation, whereas the bottom slide shows the characteristic complete dechlorination resulting in production of ethene, which is the ultimate endpoint. Now, the reasons for stalling at DC aren't just related to the absence of required microorganisms. It may be related to kinetic phenomenon where PC and DC dechlorinate much faster than the DC to VC and VC to ethene stage, and DC competes poorly for dechlorinators, so it could be just a transient phenomenon. It may also be due to running out of organic substrate. This obviously limits reductive dechlorination, and it may mean that you just need to add more carbon source to the environment. There could also be other factors as well. So, although bioaugmentation has been shown to be useful in chlorinated solvent sites, it's still very much an ongoing area for development. This list of recommendations is actually from a vendor of inoculum for chlorinated solvent sites, but I think it's a fair reflection of the current state of understanding of the need for bioaugmentation for dechlorination sites. So to wrap up this first part of the presentation, we've gone through the fundamental process requirements of microbiology and seen what the key processes that we need to optimize to maximize microbial activity in the subsurface. Given that we have a whole diversity of strategies, there's a whole range of parameters that we may want to enhance. And we've also considered this whole debate between biostimulation and bioaugmentation. Probably in summary, I'd say that we don't need bioaugmentation for hydrocarbon sites. For chlorinated solvent sites, then it may very well be a potential benefit, but you would need to evaluate that on a site-specific basis. Now, as we talk about remediation design, then it's apparent from what I've talked about earlier that there's this whole range of potential applications of in situ bioremediation. I've done a quick family tree, if you like, of bioremediation technologies. I don't claim that this is by any means complete, but it does give you a feel for the various kind of strategies that are out there, a whole range of potential alternatives. Critical to any in situ remediation design, of course, is trying to first of all understand what your goal is and how these technologies then meet your goal. So typical goals under our risk-based framework in the UK are things like source reduction. They may involve plume treatment, or they may involve plume interception as well. And I think in the context of a risk-based framework, where we're typically managing source, pathway and receptor linkages, then bioremediation technologies are available at each part of that. We can look in the unsaturated zone through things like bioventing. We can look at source treatments. We can look at plume treatments, and we can look at biological barriers as well. So this diversity in situ bioremediation approaches can actually address each element of the source pathway receptor linkage, but clearly each will have very much site-specific evaluation required to see how appropriate they are in any of these given situations. Here's a classical example of what I think most people think when you talk to them about in situ bioremediation. It's a hydraulically controlled process where we've got an extraction well taking out contaminated groundwater. In above ground reactors we supplement nutrients, we oxygenate the water, and then there's some form of reinfiltration. In this slide it's a reinfiltration gallery. It can also be reinjection wells. That inoculum, the nutrients, the oxygen, then flushes through the subsurface and is collected again, so making a cyclical kind of process. Another example, this is an in situ biosparging type scenario, where we inject air into the subsurface, into the contaminated aquifer, introducing oxygen, as well as probably in this example some physical stripping of contaminants as well. You can see there's a requirement for off-gas treatment, but just another physical variation of in situ remediation. And then finally, I guess a more recent development is this concept of biological kind of reactive zones and biological barriers. The term microbial fence was used in the early 90s, and effectively what this is the injection of biological treatment agents perpendicular to the direction of the plume. And there's a whole range of potential things we can do in that scenario. We can have solid-based systems analogous to PRBs, where the main component is a biological based substrate. We can do gas injection through diffusion or through sparging, or we can inject liquid systems as well to create this reactive zone. Fundamental to any of those techniques that I've just described really is what underpins a successful design is a complete understanding of all these parameters, starting at the conceptual site model, understanding the microbial status and geochemistry, understanding what the characteristics of your amendment are, and then working out how we're going to inject and deliver that to the subsurface. So within this design process, there's a number of key steps that I'll go very briefly through, starting from site characterization through to feasibility screening, some level of feasibility testing, and then formulation of a detailed design. Site characterization is all about scale, and I think adequate site characterization is critical to the success of any in situ technology. Many failures of in situ remediation have been attributed to an inadequate characterization of the subsurface. And typically we think of this at kind of two levels. I think there's a big picture where we're looking at the high-level operating window for in situ technologies, that's really looking at the main features of the conceptual model and deciding whether an in situ approach is appropriate. And then when we drill down, we're really looking at a detailed consideration of factors like subsurface heterogeneity, contaminant distribution, factors that really control the distribution of in situ treatment agents, because ultimately, as I've said, in situ treatment is all about getting contact within the subsurface between your treatment agent and the contaminant that you're trying to treat. The geology is a significant control on this delivery mechanism, be it in unconsolidated deposits or within bedrock environments. So, big picture, I'm sure you're all familiar with a large-scale kind of conceptual model where we're picking things up like, contaminant source information, hydrogeological information, the basic kind of parameters, the gradients, conductivity, etc. Looking at the phase distribution of contamination in the subsurface, and obviously linking that in with the risk assessment to identify which are the potentially significant linkages and what the focus of our remediation is going to be. At a site level, obviously, there is going to be much more complexity, and this is just an example of a UK site setting where, for example, we may have unconsolidated sediments overlying a fractured bedrock. And in this case, where we've got some DNAPL present, there's a large degree of heterogeneity, structural features controlling the distribution of NAPL, and a whole range of various primary and secondary sources, and a dissolved phase plume. So a complex environment that we've got to somehow assess and deal with. And just to emphasize some of the key things about these complex environments, this is kind of a classical experiment that was done. The two pictures are showing a tank that was filled with sand and some lenses of lower permeability material. The tank was then flooded with a fluorescent dye for a period, and eventually that fluorescent dye was flushed out. And really what it's showing in the bottom right hand corner is that very quickly the dye that was in the coarse-grained material, the sand, has been entirely removed from the system. But you can see that a proportion of that dye absorbed into the lower permeability lenses and is now back diffusing and resulting in a halo of fluorescent dye that is persisting within this environment. And this is very much reflecting what we see in natural environments as well. And technologies that can kind of go in and clean up these coarse-grained materials often then have to deal with potential rebound, and that's definitely a consideration in biological treatment as well. And heterogeneity is a key issue. This is in a low permeability clay environment, and you can see how these microfractures within the clay structure are actually controlling the distribution of, in this case, hydrocarbon. But it's really just meant to illustrate the importance that these very small scale structures could have on contaminant distribution, and again you were required potentially to take that into account in the design of a remediation system. and just re-emphasising this importance of matrix diffusion. Many of our major aquifers are dual porosity aquifers, things like the chalk, and in those environments there may well be this phenomenon of diffusion of contaminants into the matrix, such that when we undertake remediation of the fracture zone, there is long-term back diffusion that may well impact on the overall success of the remediation. And it's about acknowledging this and building this into your remedial design to the extent that you can. Some of the ways in which we try to overcome this is through using techniques like high resolution site characterization. Some of these tools are available in the UK now. They work on real-time principles and really assist in greatly improving the understanding of subsurface heterogeneity, allowing you to really focus in on delivery of reagents to where the contaminant mass is. And these tools include things like membrane interface probes, optical screening tools, and things like the Waterloo profiler. Other approaches that can be very useful in in-situ treatment design include the use of background fluorescence or tracer testing. When some of these tracers are put into typical subsurface environments, you can see that the actual groundwater velocities exceed predictions from conventional analysis of the data. And I think the slide in the bottom right hand corner there is from a real site where a tracer was added in a particular part of the site, and you can see the varying particle pathways and travel times from that point of injection, and obviously in addition the rate of movement compared to the Darcy kind of calculation. So I think understanding a lot of these processes is inherent as part of a in situ bioremediation design. It'll very much vary on a site specific case, but you do need to be aware of this and plan for this to maximize the effectiveness of your design. The output from all this understanding is very often a much improved conceptual site model, and really a detailed conceptual site model that's looking at the understanding of the interrelationship between the geology, chemistry and microbiology in different parts of the site, and allowing you to therefore tailor your remediation efforts accordingly. Very often, once you've completed your site characterization efforts and undertaken some initial work, the next step in the remedial design process is undertaking some kind of feasibility screen. There are a large number of various kind of matrices and checklists that you could undertake to evaluate whether your technology has the ability to meet what's your likely cleanup objective given your hydrogeological, geological and chemical setting. This is just an example of one output from that process. And you can see even at the time of writing of this that the table was very much a consensus views of the authors at the time of writing, and it wasn't meant as a generalization. And I think these things are useful as a high level screen, but very often you've got to kind of, as I say, drill down into the details of the site and really evaluate whether bioremediation can be undertaken. The key thing to come out of these screening processes are to really, raise kind of red flags that they really highlight potential issues that will need careful design to overcome them. That they may not all be kind of showstoppers, but they're certainly things that say, okay, we need to really focus on that, how we kind of going to overcome that potential constraint. And this could include things like contaminant mixtures, whether you're in a very sensitive setting, the presence of NAPL, be it L-NAPL or D-NAPL, has been mentioned when you're working in complex geologies where it's very heterogeneous or where you've got fractured bedrock. and also where you work into very strict numerical remedial targets. In order to look at the in-situ bioremediation design process in more detail, then typically we undertake treatability studies. I think it's true to say that although the general principles of bioremediation are well known, there's still enough uncertainty in biological processes and site variability that usually some form of treatability may be undertaken. There probably are a few exceptions to that when the site is well understood and where you've got a contaminant that degradation is really well known. So that may be an exception, but otherwise you probably would look at some form of pilot study just to confirm and optimize the design process. Now, treatability studies may be undertaken at a variety of levels of scale and sophistication. Typically we may look at laboratory studies or undertake pilot scale field trials as well. And what you undertake really depends on your goals, the budget, and what you're trying to understand. Treatability studies obviously normally done in a specialist laboratory. Pilot scale studies are done in the field in a portion of the site that you want to treat, where you can really focus on some of these site specific characteristics. So to look briefly at laboratory studies, these are essentially microcosms undertaken on a variety of scales on different types. The design of laboratory studies very much will vary according to your goals. You can see that it can be a very significant undertaking. The key things to consider in design are the number of replicates that you may need to get a statistically significant result, and I think critically the controls that you've got in place and whether they're actually adequate to isolate what you're trying to test. I think very often a limitation of some studies is that the controls don't really allow you to isolate the particular benefit of the treatment agent that you're actually trying to evaluate. So when setting up your microcosm study, there are a number of factors to consider. One of the key ones is the interpretation of the data and whether you're going to get sufficient information from the microcosm study to fulfill your objectives. And I've listed a range of potential objectives there, and clearly they'll need consideration in the design, timing, analysis undertaken, all factors that really need to be considered in microcosm setup. So laboratory studies do have a number of kind of positives. I think they are a very useful technique. They're useful as a yes/no in terms of can biodegradation occur. They can give some confidence in an in-situ bioremediation approach. They're ideal within a lab situation in being able to undertake a mass balance, which is often very difficult to do in field conditions. They can be indicative of the endpoint that you're going to meet on the remedial timescale, and you can screen lots of alternatives in a relatively rapid time. There are, however, potential limitations as well. Clearly, a big question mark over how representative they are of the full scale, particularly when we see some of the heterogeneity in sites, as we've already kind of discussed. These are very much kind of optimal conditions. How are you going to replicate those within the field? That is a difficulty. So what it may mean is that the degradation rates that we get in microcosms are greater than we'd expect in the field, and they don't account either for materials handling and contaminant delivery issues in the field. And I think a final thing to note is that commercial projects aren't kind of academic studies. There are budget and time constraints in the commercial world, but nevertheless I think any studies that are undertaken have got to be robust and reliable, otherwise they can be quite limited in usefulness. Pilot scale or field trials are commonly used in situ bioremediation design. Initially we may undertake conventional aquifer testing. but more realistically we'll also undertake a specific trial focused on the technology of concern. This can vary in scale from using several cubic meters to several hundred cubic meters, and it's really allowing us to assess performance, design and delivery on a bigger scale, and as I've said, taking into account actual subsurface conditions, things like ease of injection, delivery through the heterogeneity, etc. It also allows us to assess potential environmental impacts more accurately, but a downside is that it's very difficult then to replicate lots of alternatives at this stage. As I've said, the nature of trial is technology specific, and the timescale is technology specific as well. And I think when planning a pilot scale or field trial, you also need to include sufficient time for regulatory discussion and agreement and any licensing that may be appropriate. Just going to talk briefly about an example setup. This is for the evaluation of distribution of a substrate within the subsurface. So typically you'd start with an injection point, one or more injection points within the area of concern that you want to undertake the treatment, and then you'll install a series of observation points, typically in different directions and at different distances from the injection points, but also you need to put these observation points within the likely zone of influence of your injection, because you'll be relying on contaminant groundwater flow to transport the contaminants and degradation products, so you can observe the changes within the observation points. A key thing that you are trying to evaluate is the ease of injection, what flow rates you can achieve, what pressure you can achieve, whether there are any issues regarding well design, breakout of injectant, etc. And you clearly looking to evaluate the distribution of the amendment as well, whether this is through direct observation or chemical analysis, maybe using a tracer as we've seen earlier, or looking at the substrate itself. And then finally, you'd be monitoring these wells over time to look at changes in geochemistry, in microbial population, and obviously concentrations in the contaminants of concern and degradation products. An example of a field scale pilot design. Small injection cells were trialled in source areas comprising of 4 geoprobe locations where a biological substrate, in this case a vegetable oil, was injected, and the purpose of the trial was to see what was the effect of this within the subsurface, how was it kind of distributed, and did it stimulate reductive dechlorination. And the output from that was a series of graphs plotted with time that looked at both the composition of the chlorinated solvent and the natural geochemistry, and you can see that we were able to discern 3 different trends here that reflected the distribution of the substrate and its ability then to induce reductive dechlorination. And this is a typical kind of thing that you do at a pilot scale to really assess the efficacy of real delivery within the subsurface and allow you to adjust and optimize your design parameters before going to full scale. Groundwater modelling can form an important part in in-situ bioremediation design as well. As is apparent from my preceding discussion, knowledge of the hydrogeology and aquifer characteristics is a key part in in-situ application. There are a variety of design tools that incorporate the assessment of hydrogeology in design calculations. A number of these are vendor supplied, and a number are research or non-commercial applications. But essentially what they do in these tools is allow you to take into consideration things like contaminant stoichiometry, things like site hydrogeology and geology, and allow you to develop an outline design that can be used then either to input into a pilot scale trial to allow you to evaluate that, or consider in your full-scale implementation. Conventional groundwater modelling is also frequently applied to in-situ bioremediation projects, particularly where we're looking at injection or extraction systems, where you may be wanting to demonstrate the likely hydraulic capture or estimate the residence time within the reactive zone. Equally for barrier systems, again you may want to look at hydraulic capture, and if for example it's a permeable reactive barrier, you may want to look at residence times within the reactive zone. This completes our high-level review of the main aspects of in-situ bioremediation design. The output of the design process is typically a detailed design document that includes all the elements listed below. These include the basis for remediation, the engineering approach, and the requirements for monitoring and maintenance. Finally, it should also include a description of and the means of verification of the remedial goals on which the success of the system will be determined.